the converse is not true. There are functions which are D1 on an open set and yet fail to be D2 even at a single point in the set. That was my Dirichlet example. But there are other examples. Like you don't have to do anything as fancy as the D differential. Like example 7.7 I think is another example. So here I have the null numbers and I look at a function which is a differentiable. You just need to satisfy those Cauchy-Riemann equations. So I say f equal to u plus epsilon v is a differentiable, provided that you've got ux equal to vy and uy equal to 0. I say if u is equal to c1 and v is equal to c2 plus y dc1 dx, where both c1 and c2 are real functions of x alone, then that will describe the general form of a differentiable function in the D1 sense. Then I say, okay, I'm going to set c1 equal to x, c2 equal to 0. That gives me, of course, the identity function. The identity function is D1 differentiable with derivative 1. Is it D2 differentiable? All right. Well, if you look at the difference quotient for the identity function, check this out. This is the difference quotient for the identity function. What could be nicer than the identity function? And yet, equation 96, right?
Yeah.
The reciprocal is given by that.
Mm-hmm.
That's how to invert in the null numbers. And so if I try to invert the difference quotient f of x plus y epsilon, f of x naught plus y naught epsilon, I face that calculation right there. I'm using 96 to do 97.
Mm-hmm.
And when you look at what you got there, I say equation 96. So I'm saying we have to take the limit, according to the deleted difference quotient, folks, we have to take the limit along the units of the algebra, which means xy plus epsilon goes to x naught plus epsilon y naught for x not equal to x naught. Because if x is not equal to x naught, that means the real part of the variable is non-zero, which means that the inverse exists. In any event, basically this calculation here, when you understand it, shows that the deleted difference quotient does not converge. But this point is arbitrary, so we've shown that f is nowhere D2. The identity function is nowhere D2 differentiable over the null numbers. The epsilon squared term is gone because it's 0. Oh.
Mm-hmm. No.
So the point is, the thing in the big square brackets diverges as x goes to x naught.
For 97?
Yeah.
But you get the 1 out in front, so how does it not converge?
Well, that's one, but the other thing goes to infinity or minus infinity or not exist, so.
Okay, so this is that term. And, oh wait, this whole thing is no. this would be that. So this squared, boom. A is you use 96 to do 97, right?
Mm-hmm.
So you get the x minus x naught on the bottom, then that'd be x minus x naught minus y minus the y naught e over x minus x naught. And that'd be squared.
Well, the one term upstairs is literally just f of x plus y epsilon minus f of x naught y naught. Like I want to say the first bracket is just the difference of the f's. That's what I'm saying.
Yeah, that's what I'm getting confused on how you're doing the one term.
Oh.
How is this getting? Because I don't.
Okay, so like this piece right here
Mm-hmm.
is that piece. So what I'm saying is blah over a plus b epsilon
Mm-hmm.
is equal to blah times
A minus b epsilon over a over a squared. Oh, okay. So let me.
and the blah just can be put up here, and that blah is the f minus the f piece.
Yeah. Oh. Okay. Yeah, that's what I was confused. That's like.
I gotcha. So anyway, the moral of the story here is that deleted difference quotient differentiability is not a good way to study. Like, it's not very interesting
Yeah.
for
Because it doesn't converge.
for algebras like the null numbers, because like even the identity function is not there to use. If you don't have an identity function, I mean, what hope is there? Now, like I said, much of the literature on hypercomplex variables is largely centered on semi-simple algebras, and up to isomorphism. In the community case, these are just direct products of Rn and Cm. In such a context, it can be shown that the set of D1 and D2 differentiable functions on an open set coincide. And so here's that theorem. If U is an open set in a commutative semi-simple finite dimensional real algebra A, the set of D1 functions on U coincides with the set of D2 functions on U.
Sorry. So if for most of it, if hypercomplex variables is mostly in R cross C, like with wouldn't there be like a context where we could do isomorphisms on the H family, hyperbolic families?
Mm-hmm.
Right. So if we find differentiable functions on these hypercomplex variables, they should convert over to.
Oh yes, I mean that's part of what's studied, is those kinds of functions for sure. Yeah.
Oh, okay, so there's okay.
And the proof actually here involves, you take your algebra, it is isomorphic to Rn cross Cm, and I just basically study the difference quotient with respect to that isomorphism, and I show that you can get from the Frechet to the deleted difference quotient, and I think I've already proved one direction for this theorem in the previous theorem, because I already proved that D2 on an open set implies D1. So the proof to do here now is that D1 implies D2, and to do that I need to know that it's semi-simple, and so that means there is an isomorphism to Rn cross Cm, and I use that isomorphism to study the deleted difference quotient. Yep. So that's about a page and a half of stuff, and eventually I'll get it. But So this was important to me just as a step in my journey of understanding this stuff, because I found a lot of papers that take as the definition the deleted difference quotient definition.
Yeah.
But my definition is so far removed from that. How are these the same thing? Well, they are. They agree, but they don't. They agree where it's nice, and where it's not nice, the no stuff, the deleted difference quotient stuff, just not even a contender.
Consider the difference quotient.
We're now in section 8. Right?
Yeah, I'm just looking over. Wait, did I go too far?
Not far enough, I think.
Yeah.
So section 8 actually has some of those things I was talking about in terms of advanced calculus.
Yeah.
So what do we mean by a k-linear map? If you have a Cartesian product of, k copies of A, it's k-linear. Well, you could talk about real k-linearity, and then it would just be linearity in each slot in the real sense, right?
Yeah.
But I say I want to define k-linear map on A to mean that it is right A-linear in each of its arguments. So that means that I can pull out an algebra multiplication in any entry, like I say there, T of Z1 through Zj, tar of W is T of Z1 Zj Zn all times W, right? And if I can reorder the arguments any which way I like, and I don't change the output, so like for two things, it's like T of Z1 Z2 is equal to T of Z2 Z1. That would make it symmetric, two linear map, right? For a symmetric k-linear map means like you could take v1, v2, v3, and it would be equal to v1, v3, v2 fed into it. If you have the same triple of arguments rearranged in any order you like, that's symmetry. Sorry.
No, you're good.
What is fake crying? That do you hear that? Like, so the set of symmetric k-linear maps is isomorphic to A. Yeah, exactly.
No, because that's higher dimension. You can't have something that's higher dimension isomorphic to it.
Seems like it, right? That's what I was thinking to start with. But no. So we add to our list of things that are isomorphic to A, right?
Yeah.
We have A is isomorphic to the right linear maps on A, is isomorphic to the matrix representation of A with respect to a basis, right? Now, so check this out. You have T of V1, V2, Vn, right? Oh, that's a K. One.
Okay.
One.
Alright.
But we're assuming that this map is right A-linear in each entry.
Yep.
So I can pull that out.
Mm-hmm.
I can pull that out. Pull that out.
So you get T1.
T of 1 times V1 times V2. So the isomorphism from A to these, whatever you want, whatever my notation is for them, I forget. You just say psi of, t. Well, psi of. I want to go the other way around. Psi of t is t of 1, 1, 1, 1. This is not surprising because in the k equals 1 case, remember, like psi of a right linear map, t is t of 1. That's the mapping between, say, A maps to, that's the mapping between right linear maps on A to A. We had evaluated the identity. That's the isomorphism, essentially.
Yeah.
Same here. But it does seem odd, doesn't it?
Yeah, because
You're right. So bilinear maps, generally speaking, the set of bilinear maps in a vector space is as large as like symmetric matrices of the same dimension. So like symmetric bilinear maps on 3 dimensions is like 1/2 n squared plus n. So there's 9 plus 3 is 12. 12 divided by 2 is 6. Just like 3 by 3 symmetric matrix is 6-dimensional. The diagonals and the off diagonals are matching.
okay.
So you can make a correspondence between symmetric matrices in symmetric bilinear forms. Yeah, you're right. A arbitrary, real bilinear symmetric form would not uniquely correspond to a single algebra element. What's special here is it's not just a symmetric k-linear form, it is a symmetric k-linear form on A.
Okay.
So it's that right A linearity in each entry, which is like super, simplifying. And so then I define like second derivatives in the way you'd expect, right? I think we're going to have supper at like, I'm going to make sure Jimmy's not waiting to start supper until I'm done or something. Cooking while we're talking. Right here. What? Well, she was talking about going to do recycling or something. Maybe she went. She's here somewhere. Huh. All right. You good? So we define higher derivatives in the way you'd expect, derivative of the derivative, which makes sense because the derivative is a function, right? But it becomes interesting to look at that, what it actually is, right? Now this was very surprising to me when I first found it. So let's look at the second derivative. Like when I first learned this logic, I was like, what? That's weird. Is that really?
Wait, so you just keep...
Yeah.
Okay.
So alright, so first of all, we have f from A to A, right? And f prime, we can write as partial f partial z, zeta rather, and we're going to assume that v1 is the identity, alright, just to keep things nice. And so we know partial f partial zeta is partial f partial x1 in this context, right?
Yeah, and then here you say that you keep going with that logic.
Right, so f prime is also, we can think of as a mapping from A to A, and f prime prime, which is df prime dz, is partial x1 of f prime, which is partial squared f partial x1 squared.
Yeah. And then you would do the mapping from f on f prime prime. Going.
Right, and so forth, and so generally, like the jth derivative is just going to be the jth derivative with respect to the, the jth derivative with respect to the first coordinate.
Yep.
Or if you were working in something like the direct product algebra, where you didn't have the identity as a basis, right?
Mm.
How would it look? So if we had like A is equal to R cross R, right? Where 1 is 1, 1,
Mm.
Then if we have f prime is df of 1, right? F prime would actually be partial f partial x plus partial f partial y.
Oh, that's nice.
Mm-hmm. And then f prime prime would be df prime, 1, 1, which would be, let's see here, partial x, I'll use fx plus fy, that makes stuff do a little less writing. So like, that would be fxx plus 2fxy plus fyy.
I mean, this is very similar to like normal. Oh wait. Yeah.
Uh-huh.
But yeah, well, this is R cross R, so I mean, if the algebra is isomorphic or the algebra equal to R cross R, should be really differentiable like this, right?
Yeah, I mean, this is, you could also write this as like partial x plus partial y squared acting on f. So it's not so different as it
Yeah.
first appears. It really ends, because this is, you know, partial x1. Did I say squared? I meant to the j power.
Yeah.
Sorry about that. But
No, I thought that said J.
now, so when you deal with higher order derivatives in advanced calculus, like I was telling you before, if you want to talk about the kth derivative, you do something like I don't know the notation, but something like dkf and h1, h2, hk. And so this is the so-called iterated differential.
Mm-hmm.
It's a k-symmetric, multilinear, k-linear, completely symmetric form on the k-fold product of the tensor space. And so here in this context, since we identify A with its tensor, with its tangent space rather, like A and TA were staying the same. Like advanced calculus would suggest that this is the sum I1, I2, I, K, partial K, F, partial X, I1, partial X, I2, partial X, I, K, H, HI1, HI2, HIK. So this is just like standard multilinear advanced calculus. There's nothing about A calculus here. But in the context that your function is A differentiable, right? Then, as we discussed, that makes when the function's A differentiable, that actually makes this a k-linear map on A. All right. So, assuming that we have that, then this is actually just, you know, the kth derivative of f on, you know, partial. I mean, I'm going to assume we're with the identity again. Partial x1 to the kth, you know, h1.
On H.
Yeah, I'm trying to think how to write that.
But you could change X1 to H1. No, never mind.
Yeah, that's not what I should say here. Just give me a second here to dial it back. What?
Are you recording?
Yeah.
Because I'm gonna.
It's fine. You can turn the dishwasher back on too.
What?
I think the dishwasher got turned off.
You turn it off or you turn off yourself?
I turned it off. So in particular, the dkf of the basis, v1, v2, well, let's not say v1, let's say vi1, vi2, vik, right? In that case, when you feed that the basis, that makes these component functions like chronic deltas.
So they were, okay.
So they're just what that means is like this is just going to be,
Go to 1 if they're equal to 0 if they're not.
right, so it just makes the index structure down here
Yeah.
match those when you look through it. So that, but if on the other hand, this is also, if the function is a differentiable and is also k times differentiable, then it turns out that this I can rewrite as, you know, partial k f partial x1 k full times, right? Times v1 vi1 times vi2 times vik. And so this gives us like you know, an extension of the Cauchy-Riemann equation to higher order things. But actually, I think the proof of it, I actually proved this by just differentiating the Cauchy-Riemann equations and then pointing out that that implies that this differential is in fact right k linear. Like, here, let me do the second order case, right? You know, partial f partial xj, right, is partial f partial x1 times vj, right?
Yep.
What happens if I differentiate this with respect to something else, like partial squared f partial xi partial xj, right?
Do the same thing, but.
I have partial xi of this, right? So what happens there? Well, I got partial f partial x1 times vj, and that's it. I mean, plus another term, right? The derivative of vj with respect to xi is what? It's 0, right? I mean, it's constant, so I don't need to write down the other term. I can think of this as a product of two functions, so I can use the product rule.
Okay.
All right. Or I could go back and I could prove that you can pull constants out to the right just as well as you pull them out to the left in the differentiation. So then we can flip this, right? This is partial x1 of partial f partial xi.
You can have a banana, yes.
I can do that because we can switch partial derivatives
Hold it there.
for a. I am assuming that we can differentiate f as much. I'm assuming f is smooth
Yeah.
in the real sense. Okay. Now, what can I do then? If I've got derivatives like I can go that, okay, well that's partial f partial x1, right? Times vi, falling back on those Cauchy-Riemann equations.
Yeah.
But again, the basis is constant. So I can just as well write this. So in fact, I think it's calculations like this which justify the claim that this differential is actually k-linear, because you can sort of just take this thing and do the outermost, like just kind of systematically apply Cauchy-Riemann equation over and over k full times to eventually generate this multiplication.
Well, that's nice though.
It is very nice.
Yeah.
So this is equation 113. Which I guess I should point out, you can also write this you can alternatively just express as the kth derivative. It's the, you know, K primes.
Hey, that is my side.
What? What's happening? Oh no!
I told you I was.
You told me.
I told you I was.
You told me, Mommy. You told me. I'm being tolded. Oh, I hope these machines are not going to get me. Yeah, you bet, man. Oh, Jenny, you see that?
What?
I didn't see him. He goes. That's a new one. I have not. He's not been. It's not been signaling that he's watching me like that before. Now, I was gonna say, where's my? I was looking for my Taylor theorem. Is that later in this? Oh yeah, it's section 8.2. We'll get there when we get there. All right, so now we're getting somewhere. Check this out. If the sum over bij, vi star vj is equal to 0 in the algebra. So this is an equation in the algebra. All right, if you have an equation which is true in the algebra. And if f from A to A is a differential, then the sum ij of dij partial squared f partial xi partial xj is equal to 0. In other words, the equation in the algebra implies a partial differential equation for the functions of the algebra.
Is that because you can rewrite? No, but you need a partial.
Ah, yes. So here's the proof. So you start with the equation, right? And we're going to assume commutative.
Mm-hmm.
Okay. I think I said that at the start of the section, like somewhere. Commutative. What's wrong with me? So just, take your equation and multiply by partial squared f partial x1 squared. Partial f squared partial x1 squared times 0 is just what? It's 0, right? But what's this?
We know that. That's different to boo somewhere up here.
So work right to left.
Yep.
Partial squared
Right.
f.
Partial xi, partial xj.
Yeah.
Okay. So we know that, yeah,
Yeah, that's it.
yeah. Huh.
So, H3,
Okay.
right? What do we know? We know 1 minus j times j squared equals 0. We know j minus, well no, we know j squared minus what times what times what times
1 times j.
1 times, oh, 1 times
Or j squared times.
j times j, right?
Yeah, j times j, that's right.
That's 0. We know j minus j squared times j squared is equal to 0. Those are all equations which are true in H3.
Yep.
So our algebra variable and our function and usual notations out. But so of course this can be written as one's Oh, I do need, sorry, that's 1 squared.
Huh?
That was 1 squared.
Why one's, oh, no, no, still off.
Well, 1 times 1 is 1 squared. Well, I'm trying to write equations of this form, which are like, you know, the basis here is v1 is 1. That was supposed to be 1. v2 is j, v3 is j squared, right?
Mm-hmm.
So I'm trying to write equations like this, you know?
Okay, so for the first one, we get Vij times.
So this would be like v1 minus v2 v3 is 0, you know?
V1. I mean,
1 squared.
yeah.
1 times 1.
So what's the Vij term? Let's just start with that. That's,
Oh, that's just numbers.
okay.
So here, like v1 is the 0 is 1.
Yeah.
v2 3 is 1. All the others are 0.
Okay. Okay, but so for Vi times Vj, we would do for the first one, for the second, that one you get 1, or yeah, V1 times
Yeah,
Vi,
I need to rewrite that as like.
or V2 times V2.
I'm sorry. Let me try this again here. J squared times j squared
Yeah.
is minus what? That's j to the 4th. So I should be like minus 1 times j perhaps, because that's, yeah, I can do that, right?
Yeah.
And j times j, right?
Mm-hmm.
Is j squared and
J squared.
1 times j squared, right?
Yeah. And shouldn't you write that one the other way around then? J times j squared minus 1 squared. 1 times 1.
You could go either way.
Okay.
I mean, but yeah. So my point to you is these are equations that are true in H3, right?
Yeah.
So this says that like fxx minus fyz equal to 0.
Yeah.
And this says fyy minus fxy, excuse me, fzz, right? Minus fxy equal to 0. And this says, of course, fyy minus fxz equal to 0. So these are examples of what I would call a Laplace equations of H3. Now if you go back to that example we looked at earlier in section 6, remember I told you they weren't motivated at the time.
Oh, yeah.
Equation 89. Look at equation 89 now. You got your
Oh, yeah.
xx minus
Yeah.
yz, yy minus xz, and zz minus xy.
Okay. Yeah.
Incidentally, you also see the symmetry between the x and the y and the z components here. Like there's this kind of like cyclical symmetry that's flowing throughout this algebra. But so it's almost too easy. Right? So like in the complex numbers, we know I squared plus 1 equal to 0,
Yeah.
which is why fyy plus that's 1 squared, right? fxx equal to 0. That is the standard Laplace equation, you know. In H2, right, we have j squared minus 1 squared equal to 0. And that's why a H2 differentiable function will satisfy fyy minus fxx equal to 0. This is the H2 Laplace equation, but it's also what's called a wave equation. That's what wave equations look like in physics.
Yeah.
I will show you.
Yeah, no, because I was just looking at it about Schrodinger's, the Schrodinger equation, which is a wave. It just has a plus, but same thing.
Actually, the way I present the result here in corollary 8.8, I say generalized Laplace equations can be assembled mimicking patterns in the multiplication table for A, by matching patterns in the Hessian matrix. I actually don't do this much anymore. The reason I did it this way in the paper is because it was done by that way. It was understood that way in Wagner's paper, which is from like the 40s or 50s. But that's another way you can kind of see these patterns. See if you compare the multiplication table in H3 to the second derivatives, the Hessian matrix there. If you match them up, you know, like j equals j squared equals j squared, 1 equals 1.
Which equation you're on?
115.
Okay, sorry.
If you look at that, you
Oh,
can
yeah.
see, for example, fxx equals to fyz.
Yeah.
You know, that's this one. Or fxx equals to fxy. y, that's, no, excuse me. So, so you can compare like the j components, 1, 2 versus the 3, 3, that gives you fxy equals to fcc. So just like match the tiles with j,
Yeah.
then they have to match in the Hessian as well. That's another way to interpret the result that we just provided. Anyway, there's that. Now, I actually don't like this way of thinking about the result, the way I show, I mean, this way, in example 8.9, 8.10, like this drawing tables and like matching. I mean, it's okay, but like to me, this is just so much better. Whatever. Example 8.11, I think, is one of my absolute favorite examples I found. And it's partly a modification of something I found in a paper by Waterhouse, which is like from 1990 or so, I think. But the wave equation we see in physics is c squared uxx equal to utp, where c is the Planck's constant, which characterizes the speed of the transverse waves in the medium, right? So I start out with that point. I start out thinking, okay, my wave equation, c squared, how do we go?
UXX equal UGT.
So this is just a wave equation, right?
Yeah.
And so my goal in this example is to understand that wave equation in view of calculus over some algebra. So I'm going to reverse engineer the algebra in view of the PDE.
Okay.
So like my first thought is, I want this to become an equation in my algebra.
Okay.
So if then the question is like, I say what rule, I'm going to look at xt, I'm going to look at my algebra, things of the form x comma t equal to x plus t times k, right? Such that k satisfies what? I mean, what rule should the algebra element k satisfy? So I'm gonna make 1, 0 be the identity in the algebra, right?
Okay.
Well, okay, so if 1 is the identity in the algebra, then through the theorem, this tells me what it tells me. I want the equation c squared equal to k squared. So that's what I need. So I'm going to set k squared equal to c squared. Right? So that's I'm going to define my algebra subject to that rule. So in particular, I'm going to say c equal to, x plus tk, such that k squared equal to c squared, x and t are real. Right? Proceed normally, that's my algebra. Right? And then, I'll say, oh, okay, well, you know what? This algebra, this only appears to be different than an example we already know. See, because if you look at this equation, right, I can recast this as just what? K over c squared equals to 1, right? So K over C is pointing toward J. I should be able to build an isomorphism. To the hyperbolic numbers. All right? And I claim that you can use the isomorphism gamma of x plus kt let's see here, so what do I do? I think I just multiply. So if, this means that k is also equal to j times c, quote unquote. So that informs this isomorphism. I'm just going to write x plus jct. So this isomorphism, well, this mapping maps k to jc. So like k squared is j squared c squared, which is c squared. So k squared equal to c squared under the map, it satisfies, it preserves that relation like we talked about last time.
Yeah.
But remember, we also have an isomorphism of the hyperbolic numbers in the direct product algebra, right? Remember, we can do psi, I call it psi inverse from from H2 to R cross R, and that is psi inverse of x plus jy is x plus y, x minus y. Remember that one maps j to 1 comma minus 1. We studied that map before. And so if I combine these two, I can make phi equal to, how's it go? Psi inverse composed of gamma. And that's going to be a mapping from my WC algebra to H2 to R cross R. In other words, the algebra which is naturally suggested by the wave equation is isomorphic to the direct product algebra. Here's the formula explicitly. Phi of x plus tk is equal to x plus ct, x minus ct. When you compose those two isomorphisms, that's what happens. Now, remember that theorem we had last time that any A differentiable function can be written as a B differentiable function?
Mm-hmm. Yeah, because
Provided the algebra is isomorphic. So if f is an element of the differentiable functions over the WC algebra, then there exists big F in the R cross R differentiable functions, right? Such that F is equal to, now see, I've erased my picture, but let's see here.
I'm trying to find it.
Well, big F goes in the middle, but I gotta put a phi inside and outside there.
I don't think this is it, but it says, how can you change gamma to basis to beta?
See, it's this one here.
Yeah.
It has to be this, Aldrich, because phi is the isomorphism that goes from WC to R cross R, right?
Yeah.
This is a function on R cross R,
Yeah.
an R cross R differential function.